Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, good afternoon, everyone. So, just yesterday this morning walking through the building, I saw many people in unexpected places at MSR have copies of James' book on Markov chains. So, not just in the theory group, it's extremely influential, but today he'll talk about something else. Variant of DLA, Hastings-Levitov aggregation in the small particle limit. James Norris, please.
So thanks, Yuval, for the chance to talk, and more generally, thanks for the opportunity to spend some time in this beautiful place and very stimulating environment. Before I go any further, so I've not written it on the slide. This is all joint work with Amanda Turner, who was a PhD student in Cambridge and is now a lecturer in Lancaster University in the UK. Okay, so DLA is a famously hard problem, and I'm not really going to talk about DLA, but what I've got to talk about is, I suppose, motivated by it. So I want to explain in what respect the model I'm going to talk about shares features with DLA and the kind of other ways in which it's different. But let's think generally about well, I kind of describe what DLA is, or what we're trying to do with DLA. It's a model for the growth of a cluster. So in mathematical terms, you could think about a cluster as being represented by a compact set in some Euclidean space, and it's growing. So we've got a parameterized family of compact sets, which are getting bigger. Okay, so K sub t is how big the cluster is at time t. And the mechanism by which the sets grow, this is sort of physics rather than mathematics. We're imagining lots of sticky particles wandering around, and every so often a particle bumps into the cluster and sticks there. So the particles are, say, moving, the simplest, one mechanism by which you might think of these particles moving is that you set them off a long way from the cluster and they just wander around randomly like Brownian motions. And then the first point that they hit the cluster, they stick there, and the cluster grows a little bit. Okay, so the distribution of the point which the cluster will grow at is given by the hitting distribution of Brownian motion from infinity, otherwise known as the harmonic measure from infinity. Okay, so the idea is that we should make the clusters grow so that the growth rate at any point on the boundary is proportional to the amount of the harmonic measure which sits there. And immediately you can see that if you have some boundary which has fingers pointing out, then those fingers are more likely to be hit by this Brownian motion than some point deep in a fjord of the boundary of the cluster. So you expect to see that the tips of the fingers will grow preferentially. And then that's already giving an idea that, suppose you compare the growth from a nice smooth ball or disk and from something on the other hand, consider a nice smooth ball or disk with a little pinprick poking out, very small. That pinprick will get preferentially grown, so that these two domains, which are very close to each other, their evolution might therefore, not be close to each other, because this all that's required is this little prick out of the boundary in order for it to have a completely different evolution. I say this is not mathematics, but this is just some sort of heuristics. But it, if you try to make sense of a PDE story for the growth by harmonic measure, it doesn't work. You try writing down a PDE, it's not well posed. You can't do anything. And indeed, when you look at physical instances where the growth you might reasonably think of as being caused by this sort of mechanism, they look random, right? So you wouldn't expect it to come out of a PDE. They exhibit sort of fractal and apparently random features. So maybe PDEs aren't the way to go here. Okay, so I mean, which is interesting for probability, because often a sort of particle picture of what's happening, you can move over to a PDE picture, and the essential aspects of the dynamics are captured by the PDE. But here it seems it's not going to be that kind of setup. So instead, we might start with a particle model. After all, that's the kind of where the sort of physical picture began, and see what happens as the size of the particles gets small. Okay, I mean, is there any kind of limit object? Okay, now I'm going to work exclusively in 2 dimensions, which of course is already a big disappointment, because we would like to be able to understand this in 3 dimensions. But 2 dimensions is great because you have all the mechanisms of complex analysis at your disposal, and you can play lots of games which you can't do in 3 dimensions. It's this is the era of 2-dimensional probability, and so we're going to be working in 2 dimensions. So because I'm thinking about gone from thinking about a continuous evolution for now towards thinking about one which moves in discrete steps. My time parameter is going to be discrete, and I'm thinking about a sequence of compact sets which grow. K0 is always going to be the unit disk, and I'm going to progressively make it bigger by adding bits to it. I'll assume that the exterior domain from my sets is always simply connected, and then a first exploitation of the fact we're working in the plane is that I can encode the cluster through its complementary domain in terms of a conformal map, because there's a unique conformal map which takes the exterior domain of the unit disk. So here's my that's K0 unit disk, and so that the D0 is the complementary domain. We'll get mapped by some conformal map to the complementary domain dn of the cluster at time n. Because there's a 3-parameter family which does this, but there's only one which has the property that it fixes infinity and doesn't rotate the plane at infinity at all. So come up with the unique conformal map associated with these 2 with this cluster. Okay. You know about the conformal invariance of Brownian motion? If I take a Brownian motion in 2 dimensions and I look at this image under a conformal map, then up to a change of time scale, I'm still looking at Brownian motion. So in particular, if I'm thinking about hitting probabilities, if I start a Brownian motion off at infinity here, or if you like on a sort of large circle around here uniformly, well, actually I know then that it's going to by sort of symmetries of Brownian motion, I know that the hitting distribution here is the uniform distribution. If I map this over here, then I'm again looking at a time change of Brownian motion. So it's the hitting distribution of the image process on here will just be the harmonic measure from infinity. And so this shows us that if I take the uniform distribution here and I map it over, I'm assuming the boundary is nice here, boundary of this domain is nice. If I map it over, if I put the measure over here using phi n, then I will get exactly the harmonic measure on the boundary of this cluster. Okay? All right, so this slide describes the, well, actually a big family of models. We were discussing just before the talk that, in some sense, this kind of prior work on this family, not all of it published by Carlson and Makarov, but the name which has become associated with the family of models, the names are Hastings and Levitov. So these are models for aggregation, for kind of growth of clusters in the plane, which are encoded using conformal maps. There's a one-parameter family of these models, parameter alpha. I'm actually going to talk exclusively about alpha equals 0, which is the easiest one to study of this family. So it's work in progress to deal with the other alphas. How far we'll ever get, I don't know. There's a recent preprint of Amanda and Frederick Johansson and Alan Solar, where they've begun to make made a bit of progress with positive values of alpha, just posted on the archive. But for today, it'll, apart from this slide, be entirely about alpha equals 0. But let me describe the whole family so you can see see what it is. Okay, so I'm going to consider adding a certain sort of particle to the unit disk. And two simple examples you might want to keep in mind are, on the one hand, I could think of adding a slit like that of length delta, or I might think of adding a little ball of diameter delta. So that's a family of particles, because I could think about varying delta. Okay, now if I just exaggerate this picture a little bit, suppose that Kn was like that. Right. Now, I really want to attach a particle here of some certain size, say delta 0, where the attachment point is chosen according to harmonic measure. Okay, so I might want to attach a little ball here. But what I'm actually going to do is to attach a particle at some random point on the circle, and then I'm going to map it over using phi n. Right. Now, the amount of harmonic measure on this little bit of boundary here is quite small. It's hard for Brownian motion to get in here. So when I map it over here to the circle, it maps to a small interval. So in order to have a particle of size delta here, it would have to be much smaller than delta over here, right? Because there's a scale factor of, if it's attached at angle theta, if this is e to the I theta, that's the scale factor in moving in this direction. So I'd want to add a small particle there. And if I was adding a particle of size delta here, well, this little bit of boundary here has got lots of harmonic measures, easy to hit. So over here, I'd want to attach something which was relatively get this right. Yeah, relatively large over that. Okay, so actually motivates the formula given here. That my delta n's over on this side. I take a ball or a slit of size delta n plus 1. This is the pointer, right? Do anyone know which button is supposed to activate it?
Are you sure this is the pointer? Don't you have like a silver pen?
Okay. So, all right. So take my basic particle size, and then I adjust. If I take alpha equals 2, it does the adjustment I was describing. Alpha equals 2 scales down delta so that when the particle is mapped back to Kn, it comes out at the right size. So we should aim to get all the particles of the same size over here when alpha equals 2. Okay. When alpha equals 0, you don't bother to do that, so that although the particles are the same size over here, we're going to end up adding different size particles over there. And we might want to explore how things varied as we let alpha go between 0 and 2. Obviously, alpha equals 2 gives you your best hope for something which looks like DLA. It's believed that actually the whole family of models is of interest, and possibly the alpha equals 0 is some sort of connection with the Eden model, which is another famous growth model in probability.
Alpha equals 1.
Alpha equals 1, sorry, yes. Alpha equals 0, you can see it's going to be much simpler because I'm not doing anything here. And that's the one we can do something with. All right, a little bit of light relief. Why might you be interested in this sort of thing? Here are some pictures of instances, either physical or computational, where clusters are grown, and they show interesting features. They don't look like balls. They look random, and they look kind of fractal. Mathematics has not really had much success yet in explaining what's going on here, but I think it ought to, right? There's some math to be done here. So these are caused by some sort of electrical effect like lightning. Lichtenberg figures, famous source of paperweights. There's a different sort of growth model coming from biology. You can see sort of fingers coming out, but I mean, maybe this is growing more like roughly like a ball, but it's a simulation of DLA. The colours in these pictures encoding times at which particles are added. And this is a simulation which Amanda did of our model, HL0. It's not too different to this simulation of DLA. Again, the colours are encoding different epochs at which one is adding particles. Okay, this slide just reviews the model, which is going to be the subject of the rest of the talk. So if you've got if it's something you kind of want me to explain, then I'm happy to take questions. Start with the unit disk and fix a parameter delta. Delta in the end is going to go to 0. We're going to be thinking about scaling limits as the size of the particle goes to 0. The particle I add at each stage will either be a slit. Decide once and for all whether to look at slits or disks. The picture here was this picture was the slit model. Then there will be some unique conformal map which kind of encodes adding that particle to the unit disk, subject to these normalizations. And the way the model is constructed is the following. It's the probability comes from a sequence of independent uniform random variables on the unit on interval from 0 to 2 pi on the circle. Theta is going to be the angle at which the particle is attached on the circle. And probably the best formula to look at to understand what's going on is this one. P is my basic particle, could be a little disk attached at the point 1 on the unit circle. Then you rotate the disk by a random angle, and then you map it over to the cluster using the conformal map, phi n. So you end up with a new bit added to the cluster. As the cluster evolves, you add more and more particles. The challenge is to understand what the limiting shape of these clusters, describe the stochastic structure of the clusters which form in this way. So I mean, maybe one thing to say is this: the parallels here with the with SLE, right? So if I look at the inverse map, then I kind of get the composition in the right order for a stochastic flow. Oh, maybe I did inverse, isn't it? Perhaps this is not too visible, but so the inverse maps of these conformal maps are stochastic flows. I can put a point into the flow and see it evolve, and this will follow some Markov evolution. And this, I mean, you know, in SLE, you want to study either the trace or the hull. What you actually get access to it through is the Loevner flow, and much of the hard work is to translate stuff you can prove for this into properties of this. Okay, and that's kind of exactly paralleled in the maths we do here, that we can understand this map pretty well, and then we work hard at it and are unable to understand the inverse. Okay, so this is the theorem on the shape of the cluster. Let's see what it says. The stuff at the beginning isn't so important. You should look at these 3 bullets. We're really interested. So this describes how the cluster has evolved after a certain number of iterations of adding particles. Delta. We're considering the limit as delta goes to 0. The size of the particles becomes small. When the number of particles, when you've added a number of particles of order 1 over delta squared, you've grown in fact, approximately a ball of radius, some macroscopic size. So the interesting values of n in this theorem are really when n is like 1 over delta squared. Because if you scale down the size of the particles you're adding, then you need to scale up the number of particles you add in order to see anything appreciable happen. And the way that you need to do the scaling is this. Okay. So what do the 3 things say? Well, the first one says that when we add a particle, then in fact it ends up close to a scale-up by the current size of the cluster to the point at which it was attached on the unit circle. So we attached a point at the unit circle, we mapped it over to the cluster. It turns out really just to be kind of moved out and scaled up. I mean, this is despite the fact that the cluster has an extremely complicated boundary, and in principle it could be attached anywhere. The particles don't get attached just anywhere, they just get attached kind of on a scaled up version of the unit circle. Okay. And the particles don't get distorted hugely. They're all close to e to the Cn plus I theta n. The second thing says there aren't any big holes in the cluster. So any point which is within the kind of approximate shape occupied by the cluster, there is some bit of the cluster, Kn, which is close to it. So we fill out a disk. And the second one is simply saying, well, this accounts for where all the particles go up to a certain maximum value of n, which can be taken to be pretty large. Remember, it's n delta to the minus 2, which is really of interest, and so this is much larger. But this is just saying that none of the other particles penetrate into kind of. The particles are all attached in the boundary layer. It's a growing disk, and you never get a particle which is attached kind of further in than it should be, beyond an epsilon. Okay, so the limit shape is a ball. It fills out the ball, and we have some good control about where the particles are attached, and there's a final cluster. Okay. Right, so that's one level of description. Disappointing in a way because it's a deterministic limit. All right, and we were hoping to see some sort of random effects as delta goes to 0. Right, so the rest of the talk is about discovering some random effects in the cluster, which you might anticipate by looking at the picture here. So we're trying to describe this by a theorem. What is there to say? Well, I mean, you can see bits of it are picked up by the theorem I just stated, that it fills out the disk. You can see that as time goes by, it accretes in layers. But what we were able to do is to say something about the structure of these fingers. Okay. So that's really what the rest of the talk is devoted to, understanding of the structure of the fingers. To get access to that, we have to think about this thing we call the harmonic measure flow. Okay, it's helpful in understanding these things to sort of take logs in the the boundary of the cluster becomes this instead of e to the Cn, we're looking at the points this will be Cn plus I theta, and there's the boundary of the cluster there. So suppose that's the boundary of the cluster Kn, and then we add another particle, so that's the boundary of the cluster Kn plus 1. And then when we take the this is realized by some intertwining of the conformal map with the exponential function with a map from this line. So the harmonic measure parameterizes the boundary here by theta going from 0 to 2 pi. Okay, so we can map this by phi. Well, let's call it little phi n, distinguish it from the big phi n, which was exponentiated. This is parameterized by theta from 0 to 2 pi. On the other hand, so is the other boundary. The boundary of Kn plus 1 is also parameterized by theta. And the boundary of Kn is a subset of the new boundary. So there is a map on the interval from 0 to 2 pi which takes the so each point of the boundary here, parameterized by harmonic measure. So suppose that's the parameter set there, gets mapped to some parameter value in the new boundary of kn plus 1. Only there has to be a jump. The map is essentially the identity away from some little region here around the particle, but we have to kind of force in a new bit of boundary here. So you end up with this map gn plus 1, or g, what did I call it? G theta n plus 1. And so one gets a flow of the harmonic measure as you add more and more particles. And it's by looking at this flow that we can understand the behavior of the fingers. So the way it goes is that we're able to take a limit of these flows in some weak sense and understand the limit measure. Okay. In order to do that, you have to have some space in which the flows live. To do weak limits in probability, you have to understand the space in which the flows live in. So this is the space which the flows live in. So here's a picture here of a non-decreasing right continuous function which sort of repeats itself periodically. So if I consider this set of all such functions without the periodic condition, then I'm going to say two functions like that are close if when you rotate the axes, so instead of thinking of it as being a non-decreasing right continuous function, I could just draw axes like that cross, and it becomes a contraction. Okay? And if I consider two such functions, I could look at the uniform distance between those two contractions. You've got to tilt your head by 45 degrees. Okay? So, I mean, the distance of this function from the identity is just the maximum value that it ever gets away from the diagonal, for example. So instead of looking at the uniform norm, we have to look at some usual way of just weakening that a little bit by so it's kind of locally uniform norm. Okay, so the harmonic measure flow is a flow in the sense it has a kind of normal property that you'd expect of flows. That if you act by over one time interval by the flow, and then you flow on more along the next time interval, then you get what you would expect by taking the flow over the larger time interval. However, this the flow property turns out not to be robust under the sorts of topology which is possible to put on this flow space. There's a weaker flow property, which is robust, and that's written here. That these increasing functions have right and left limits, and the right way to think about the flow property to make it robust is to say when you compose the left limits over two time intervals, then you get the left limit, something which is less than or equal to the left limit over the longer time interval, and then something analogous with the inequality the other way around for the right limits. One property that a flow might have is that it would be continuous in this sense, that if you look at how far things move over short time intervals, it's not very far. Okay, so I want to consider continuous, in this sense, weak flows. And on that space, there's a way of defining a metric, which turns the space of these flows into a complete separable metric space. So there you have an object where you can start thinking about weak convergence. So we looked at that picture before. That's how you define the distance between two flows. Okay, now there's a famous object in probability, which is the coalescing Brownian flow, which I now want to introduce because it turns out to be the limit object for the harmonic measure flows. Okay, so if I start with think about Brownian motions on a circle and take a collection of starting points, and I run Brownian motions forwards from these points. And I have a rule that if I go through the starting points in turn, and if I hit a Brownian motion already there, I just join up with it. Then it's easy to see that you get something, a distribution on coalescing Brownian paths, which is independent of the order which you set things up. And you can have more and more points in here. So eventually you could have Brownian motions going from every rational point forwards. And then there's a good way to kind of complete this so that you end up with you can say, for every point on this line here, where it goes to on this line. And the sort of pictures that you end up with is that actually there are only finitely many images. Every point here actually has coalesced into one by a certain later time. And so that's what the function looks like. If you draw a graph of the function, then it looks like a staircase. Not all the same size, but the graph of this function is a staircase like that. Oh, so this is there's a theta here, and it gets mapped to f of theta over there. All of those going to that one. Okay, so this is theta, and that's f of theta, like that. Okay. So in fact, you can think of the coalescing, think of Aratia's flow as being a probability measure on this continuous weak flow space. It doesn't live, just as the sometimes necessary to complete spaces in order to support measures. It doesn't live on the space of perfect flows, but it does live nicely on the space of these continuous weak flows. This is basically a result of Aratia. It's just reformulated in the language of these continuous weak flows. There's a unique Borel probability measure on the space with the property that so this means I kind of drop a point into the flow and see where it goes. Well, it does a Brownian motion, because from this and Levy's characterization, it would imply that this is a Brownian motion. And the fact that this is a martingale says that if I drop two different points into the flow, then as soon as they hit each other, they perform independent Brownian motions, again by Levy's characterization, up until the time they first hit each other, TEE. And thereafter, they perform a single Brownian motion, because as soon as we get after this time, we have to compensate the thing by the usual Brownian drift. Okay, so this is a neat way to give a martingale characterization of the Aratia flow. Okay. this is kind of more propaganda. This is a good way to think about the Aratia flow. You can invert all these continuous weak flows. Just look at the inverse map. The time reversal map, which just takes this inverse, turns out to give an isometry of this space, and then it also preserves the law of the coalescing Brownian flow. Right. So the harmonic measure flow is going to converge to the coalescing Brownian flow. And that's because the harmonic measure flow turns out to be one of these, what we've called disturbance flows. So I can describe what a disturbance flow looks like in general. Suppose I take some basic disturbance. So I call it disturbance because it's not quite the identity. It's a little disturbance of the identity. So it looks like the identity for most values of theta between 0 and 2 pi. But then there's perhaps some little region where it's not quite the identity. Okay? And suppose that I then randomize this theta here. I can sort of move this up and down the line to vary the value of theta. Okay, so there's a particular function g. So that might be a picture of g theta. I specify g naught, and then g theta is obtained from it by translation. So I fix the disturbance g naught. Okay, and then I form a flow just by iterating with random values of theta. Okay, so this is a random function. So I choose these thetas uniformly random. How will a point move under this flow? Well, for most of the time, it doesn't move very much because you're away from the disturbance. Every now and again, the disturbance lands close to where you are, and you get moved a little bit, and it's symmetric. So you're just as likely to go up as you are to go down. Okay? So just think about the motion of one point. What's the scaling limit going to be? Well, by symmetry, it's going to be Brownian motion. Now, what about putting 2 points into this flow? How are they going to move? Well, it's going to be different times that you move the 2 points, provided they're separated. Okay? So they'll move as independent Brownian motions until they're close. And then when they're close together, they'll tend to get hit by they'll get moved in the same way by the disturbance. And so no surprise, and really not very difficult to show, at least for kind of finitely many points, that the limit object is coalescing Brownian motions. Okay? So, but in order to get the result we wanted, it was necessary to consider this limit at the level of the flows, not just the level of finitely many points. Okay, so back to the slide. So you specify a disturbance, you get a disturbance flow. You can do a sort of diffusive rescaling of the flow, which is described here. Don't expect you to kind of absorb it all, but can look at the flow on various scales. Just as when you prove convergence of random walks to Brownian motion, you need to work in the sort of Skorokhod topology to understand that as the right topology. There's a sort of Skorokhod metric on the flow space, and in that metric, the rescaled disturbance flows converge weakly to the coalescing Brownian flow. Okay, so the limit of disturbance flows. So this is kind of a nice way to think, to realize the coalescing Brownian flow. In fact, I guess I should explain what these criteria are. So one of them expresses that the size of the disturbance is becoming small. And the size of the disturbance is smaller than the scale at which we are trying to look at the flow. Okay. Now, the harmonic measure flow, the flow of the harmonic measure on the boundary of the cluster, turns out to be exactly one of these disturbance flows. And so that flow converges to the coalescing Brownian flow. That, in fact, we knew a long time ago. But then, by combining that with the sort of precise location of the clusters, which is given by the other theorem, we're able to transfer that information about the harmonic measure flow to the shapes of the fingers in the cluster. Okay, so this slide is just saying that the harmonic measure flow is converging to the coalescing Brownian flow. Now, I want to talk about the fingers. If I take any point in the cluster, there's a notion of ancestry. Okay, because the particle attached to another particle, and you can trace back in time and watch where your ancestors were. Okay, and they won't go sort of straight radially into the unit circle. They'll move around a little bit. So the finger of a point is its ancestral line in space. And I've drawn this picture in the sort of logarithmic scale. There's also an escape route associated with a point. If I take some point and attach a piece of thread to it, and then that thread leading out of the cluster through the gaps between the particles, and I pull that thread tight, then I get a unique path from that point out to infinity, outside the cluster. Okay, so for any given point, there's a finger going in, and there's an escape route going out. Okay.
This escape route is just line segments and circle arcs.
This is misleading because these have all been distorted by the conformal map. But essentially, yes. I mean, the escape routes will have line segments and also bits which are round particles. Yeah. Okay. So because we know essentially where all the particles are by the earlier theorem, we can establish the limiting shapes of the fingers and the gaps by referring the particles to their thetas, which are coming from the harmonic measure. So in the end, for example, show that if I take a finite collection of sort of space-time starting points, so those will be points in this diagram, and consider for each point the finger going in and the escape route going out. So there are two paths associated to each starting point, one going forwards in time, one going backwards in time. So that gives a probability measure on, I guess, paths which, finite collection of paths which coalesce both when you go forwards in time and they go back and forwards in time, and when they go backwards in time, because the fingers tend to coalesce, but also the escape routes tend to coalesce, right?
The fingers coalesce one way, the gaps coalesce the other way.
Yeah. Should draw a picture. There you go. Theta from 0 to 2 pi. It's a collection of points to start from. We trace back the finger here, and this finger, which may join up with that one. Okay, and it's a good time to have a. Then you trace the escape routes for this. So the cluster is all over the place, right? So your escape route is very much constrained by the cluster. There are no big holes in the cluster. Here's the escape route for this one, like that. All right, so this escape route is coming out here. There are more escape. It's more constrained than it looks by the picture because I'm only considering finitely many points here. But here are the escape routes coalescing. Oh, is that all of them? Well, okay.
David, this can be obtained as in some version as a scaling limit of the uniform spanning tree in its dual, but this is, I guess.
So this is a picture which this is a sketch of something which is read off the cluster. You sort of take logs of the cluster and you, okay, but then this converges in a weak sense to the backwards and forward lines in the coalescing Brownian flow. That's the theorem. Okay. So we do understand the kind of the stochastic structure, and so you're supposed to kind of right. So we simulated the limit law. Didn't succeed in making it very much like so this is a simulation of backwards and forwards lines in the coalescing Brownian flow, but exponentiated around the light blue ones go out and the dark blue ones go in. So if you could see, at each point there is a light blue line going outwards and there's a dark blue line going inwards, and they all coalesce, right? So that's supposed to look like this one, which was the Hastings-Levitov simulation. Well,
but in this one you just see the fingers, not the gaps.
That's correct. You have to imagine the gaps.
Okay, but if you want somehow to match the pictures, it's good.
Sure, sure. But okay, so you can just look at the dark blue lines. You can look at the dark blue lines in there, right? And then that's supposed to look like this one considered in monochrome. Okay, so I'll stop there.
Do you know how they simulated that?
I know roughly. I'm not the one who did it. This is Amanda's simulation.
But I mean,
okay, so you basically work out where each pixel goes. The slip map, conformal map, is something explicit, right? Okay. You can just work it out. I mean, you know what the slip map is for the upper half plane, and you just move it around, and you get the slip map for the disk. Okay, so that's something you can ask your computer to do, and you can also get your computer to generate the random thetas, and then you compose and you see where each point goes. Hey, you get a picture.
It would be interesting to offer a little bit historic perspective, because this picture was not in this high resolution and so on, but was created first in the late 80s actually, and so 10 years before Hastings and Levitov looked at this. And there was a talk, the only trace that left in the literature, later Makarov and Carlson worked on this, but in the 80s actually the only trace in the literature is by a guy named Richard Rockberg, who gave a talk at an AMS conference. Mm-hmm. And the title was actually Stochastic Löwner Equation. So that's SLE. But of course we know SLE is different, but in many ways the generation of just composing a fixed conformal map with some randomness.
Yeah.
But back then, of course, the computers were very lame, slow, and pictures were never.
So, if I can add a kind of sort of personal rider to that, I mean, I was just thinking, what happens if you take SLE and you drive it by a Poisson random measure? right? And then you, of course, if you increase the intensity of the Poisson random measure, you'd expect to get back to the Lebesgue measure. If you drive SLE by Lebesgue measure, you just get an expanding disk, nothing interesting. So do you get anything interesting when you drive it by a Poisson random measure? Well, actually you do. Even when the particle size goes to 0, even when the kind of effect of each little atom in the measure goes to 0, there's still something stochastic left if you do proper rescaling. Well, of course, we know this, don't we? We look at the law of large numbers and you do a proper rescaling. I mean, these Brownian fluctuations, they're not on the scale of this cluster. They are on a smaller scale here. I reversed from the SLE to this, but then fell on this older idea of Carson and Makarov, I guess.
Yes, one more question. So, do you think one could take this and construct a model closer to SLE by building this, but still putting some, adding some artificial randomness on the size of the fingers? So, in other words, if you look at an individual finger, do you expect it to look locally like a DLA finger, or just with different stretching? I don't expect you to construct real DLA, but maybe something that will be a little more like it by building this and then kind of just growing.
Yeah. So there's another work by the three, Turner, Johansson, Sola, and Turner, where they investigate a rotationally inhomogeneous version of this this story, so that they add particles of different sizes at different angles, and that develops in a rather interesting way. I think so you could have some sort of you could cite in advance some sort of random way, or I mean, one might even try to think, how could you drive that randomness by, I mean, it would be, the nice thing to do perhaps would be to sort of use stochastic fluctuations which are kind of present in this to drive the, in a sense, putting alpha positive is doing exactly this, right? So that's a hard way to do it. So you're saying, well, you do it another way and make it look like DLA. Yes, I think that's a really good idea.
Okay, so